Okay.
Mm-hmm.
So if I had this alpha, then I think I'd do something different here. Like there'd be somehow divided by alpha there. Would be the right thing.
Mm-hmm.
And then I think this would lead to a lower noise variance. You know what I mean?
Mm-hmm. Because the scale factor.
Yeah.
Scale factor is greater than 1.
Yeah. Okay, so I'm not sure if this is right. So, okay, so what we know is that x1 of 2 minus, or say x1 minus this should equal, I would say it ought to equal just the error in E1, right? Because if I know E1, then I have no error.
Mm-hmm.
You know? So this should equal E1 minus E1 hat. But all divided by alpha, sort of. Well, let's say this is E1. This is exactly E1 here.
Just okay.
And I sent alpha E1.
Okay.
So I made an estimate of E1 hat.
Mm-hmm.
Okay, so this should be true.
Okay, let's try to write down some facts.
Okay.
To say the quality of, ultimately we're trying to measure the quality of those estimates, which is, I guess, the variance.
Yeah.
The random variables, so we want to measure their variance. So
Mm-hmm.
it seems like we should be able to write down what the, let's see, there's x2.
What's this? x1 minus E1. x1, so E1 equals x1 minus x. So x1 minus E1 equals x1 hat. So this equals x1 hat. Okay.
So you update x1 hat of 1.
Okay.
Okay. Plus, so you add in.
Yeah.
You add in the error, which is a weighted.
Okay, so now the question is, how well can I estimate E1? So what's the variance of E1 hat? I guess that's a question, right?
Yes, and what's the variance of E2 hat? Or
Right.
E1?
So I would say that this is equivalent to dividing the noise by alpha, you know? So that our effective noise variance is n over alpha squared. So then the variance of this should be Pn over alpha squared divided by P plus n over alpha squared. And so if I multiply by alpha squared, then
Alpha squared over n.
I should just get this. Right.
Yeah.
Right.
Well, the n is still there, yeah. Now we'll divide everything by n, so it's P.
Okay, so alpha squared was greater than 1.
Mm-hmm.
Or in fact, alpha squared equals n.
N over P.
Equals n plus. So this
N plus
equals
P over n, yeah, okay, good.
n plus P over n.
Times P.
What's that?
So simplify that. We need to write that as a function of n over n plus p, because we know what the variance of E1 there.
Yeah.
See, over there you have the variance of E1. You wrote down an expression Pn over n plus p. So we want to see if we've improved now with that expression you have there.
Oh, sorry, this isn't the variance of E1. This is the variance of E1 minus. So this is the new variance of this guy. Total error.
Wait, that's the variance of E1 minus E1 hat.
Yeah.
Any progress?
Yeah, I think that's getting onto something here.
A little bit of progress. Well, Jeff brought in some LQG for a problem and some books.
Fantastic.
The LQG problem seems related somehow, a little bit. So yeah, well, I mean,
What's the story? Let's simplify that
Yes.
thing there.
well, how does it simplify? I mean, we get n squared here if we wanted.
Okay.
N squared.
NP plus P squared plus N squared. Which is, so how does that compare to N over N plus P?
Oh, well, it's definitely n over n plus p or pn.
Pn, yeah, Pn over.
Oh, well, it's definitely small because alpha is greater than 1.
Okay, so what you've shown is that the
This is better than sending x1 again.
Uh-huh.
I think. Well, I'm not really
If
sure
you
what
send
you
x1
do.
again, it would reduce it by just.
Well, then you'd have to
a factor of
combine the
4.
estimates. Then you'd want to combine the two estimates of x1. Maybe you would get the same thing.
What we're trying to
But
do
it would
is
be more complicated.
compare. If you want to send x1 over a channel that adds W
Yep.
noise, we're comparing two strategies. First of all, is you send x1 and then you send x1 again. Okay, and in the second scenario, you send x1
You said
and then you send x1 minus what was
X1
received at the first time. You're able to have perfect feedback.
okay.
And we're trying to argue that with the feedback, if you send the error
Yeah.
over the same channel, that's better than just sending the same x1 again.
Okay.
That should be true. But let's see what would happen if you what is the joint estimate of x1 if we have x1, x1,
Mm-hmm.
plus w, w1, w2.
So how do you combine those estimates correctly? They're independent. Or what is the variance of that?
Yeah, we'd have to find the estimator and the variance. So I always forget what to do. But we could find the cross correlation, Can we do that? Right? Let's say x1.
If you're allowed, are you allowing yourselves an amplification factor?
Yes.
Yes.
Then why not make that something really huge? Like
Or the
Well, I
set of
want it to be
limited
comparable to the power. I want
your limit, your power limit.
power limited, yep, in
Alright.
both cases.
Okay, so what's the general formula for the, for the error variance? Does anyone know?
What if
Error
we say they're
variance.
independent?
Well, the x's aren't independent.
Yeah, the x's aren't independent, but the error might be independent.
Well, the errors are independent, yeah. These two are independent.
Those two, but the x1 minus x1 hat should be independent from x1.
Oh, no, it should be independent of x1 plus w.
Isn't it something like the error variance? The error variance.
Yeah.
Wait a sec.
Yeah, isn't it like...
Sigma.
Oh, where they do the cross.
Lambda. Oh, lambda x minus something like lambda. Lambda x. You're doing it.
Well, what's the formula for the estimator, first of all? It's lambda y times everything's 0. It's like that, right?
Right.
So this thing is the expected value of x, y,
Yeah.
transpose, right?
Yeah.
Inverse.
Mhm.
And then y. Okay, so the expected value of x1 plus w.
Oh, you're figuring. Now this is the same thing.
Mm-hmm.